So let's look at our sine graph, but extend it instead of just being from 0 to 360, and that we get the one curve, the sine is a snake on the ground here curve. We also are extending it backwards into from negative 360 to 0. And as a matter of fact, if we kept going, we could go around the circle and we would see the same curve repeat itself over and over again as we go around the circle more times. So this graph actually extends forever in both directions, in both x directions. So let's just summarize a couple things about the sine graph. First of all, the sine graph repeats itself every 360 degrees. So we say that the graph has a period of 360 degrees. That's called a periodic function. Let's also define the domain and range of the function. As we just said a minute ago, the domain is negative infinity to infinity. I could put any angle in. I could put an angle of 1,000 in. That just means I keep going around the circle, and the graph, the trig values just repeat themselves over and over and over again every 360 degrees. The range, however, is very limited. It just goes from -1 to +1, with both of those values included. Another thing we can see about sine is that sine is an odd function. It has that symmetry through the origin. If I put it opposite values for x, I get opposite values for y. So sine of 30 would be 1/2, sine of -30, -1/2. Sine of 90 would be 1, sine of -90, -1. So sine is an odd function. Now, how are we going to draw the cosecant graph? I made a table of values for some of the values for the sine graph. Values where the sine value is either 0, 1/2, or 1, or -1/2 or -1. So these are the points that I'm focusing on. And I can see those same points repeated. They would be repeated here, here. Okay, so all of these points also would be the same trig values, just repeated again on a different cycle. Now I'm going to key in on those points and find the reciprocals of each of those points. So recall that when we multiply a number times its reciprocal, we get 1. And we can see that just by looking at the definition. If I multiply sine of theta times cosecant of theta, that's the same thing as multiplying sine of theta times 1 over sine of theta. So I just get 1. So I'm looking for values, trig values for sine and cosecant that multiply to give me 1. So here I have a chart. Sine of 0 is 0. Sine of 30 is 1/2. We already saw that if sine of 30 is 1/2, then the reciprocal of 1/2 is 2. So cosecant would be 2. That's going to also be true for 150. For 210, the reciprocal of -1/2 would be -2, because -2 times -1/2 would give me 1. So that at 330, the reciprocal would also be -2. Now what about 1 and -1? The reciprocal of 1 is 1 over 1, which is still 1. The reciprocal of -1 is 1 over -1, which is still -1. So if I multiply 1 times itself or -1 times itself, I get 1. So those are reciprocals. Now the tricky one we have here is 0. What is the reciprocal of 0? Well, if we think sine of theta is 0 and cosecant of theta is 1 divided by sine of theta, it would be 1 over 0, and that's undefined. So that makes sense because there is no number that I can multiply times 0 and get 1. So 0's reciprocal is just an undefined number. We know that if the output of a function is undefined, that means for that particular x value, in this case our x value are our angles, theta, our output value does not exist. So we're going to put asymptotes at 0 and 180 and 360, and also at -180 and -360, because those are all the places where sine of theta is 0, so cosecant of theta doesn't exist. Then we notice that every place that sine is equal to 1, so is cosecant. And where sine is equal to -1, so is cosecant. Those are going to repeat at -90 and at -270. Those are places where the sine and the cosecant value are equal to each other. The last group of points are the points where sine is equal to 1/2. Sine is equal to 1/2 at 30, so cosecant is equal to 2. Sine is also equal to 1/2 at 150, so cosecant of theta is equal to 2. Then if we go into our quadrant 3 and 4 angles, sine of 210 is -1/2, so cosecant of 210 is -2. Sine of 330 is -1/2, so cosecant of 330 is -2. So what I get are some pretty much U-shaped graphs that fit in between the asymptotes. They're not parabolas, they're more U-shaped than a parabola is. And they also don't continue to extend out forever. They're contained within their asymptotes. We could also plot those same points. -30 and -150 would also have cosecant values of -2. There's symmetry to this graph. And -210 and -330 would also have cosecant values of -2. So what you can imagine is if I were to draw the cosine graph on this same grid, the cosine graph would actually kind of fit inside the cosecant graph like this, only sharing points at the maximum and minimum values of the curves. So this would be f of x equals sine of x, and this would be f of x equals cosecant of x, or theta. I'm kind of using them interchangeably, x or theta. So this is the sine graph, this is the cosecant graph. So you can see if I know what the sine graph looks like, I could easily draw the cosecant graph. But realize, this is not part of the cosecant graph. This red graph, this is a totally separate graph. This is the sine graph. But notice how it just fits right inside. That makes it really easy to draw the cosecant graph.